So, good morning, sir. This is case study for a safe and efficient lane change decision making strategy of autonomous based navigation. So, on deep reinforced learning. So, here, what is meant by reinforced learning is for each and every move we get and reward to get to the destination. So, this is actually we studied about reinforced learning in the last sem, and I have 8 papers here. This is my paper where I given us earlier in the introduction. So I just come up with every. I will show you first what are the papers I used here. So this is my second paper, like in 8 different papers. In the 8 different papers, this is the first paper, and I have given everything like overview and objectives and methodology and the limitation for everything, and finally I given what are the limitation to be overcome, and I got the solution to be known, and with these are the comparative analysis for the paper, and overall I given the problem statement and given the solution for this. So let me start with the my paper, and yeah, okay. So my paper is truly based on the how we are going safely without any crashes or bumping each other with the vehicle. So this is the paper. So author name is Ching-Win Zhao and Ainsberg Zhang, Rui Zhang. Okay, let me comment the overview. This paper proposes a deep learning and learning based lane change decision making framework aimed at achieving safe and efficient lane changes in autonomous vehicles. The strategy focuses on evaluating the risk dynamically and incorporating vehicle interaction behavior into the decision model. So objective to create an, as I told earlier, create a real-time lane-changing decision-making without any bumping or something. So for that I given a balanced safety, efficiency and comfort. And yeah, for an autonomous vehicle we need a surrounding behaviors, right? So in order to go safely in the traffic behaviors, we just need to have some protocols like proactive lane change decision using DRL. And given the methodologies, state space design like ego vehicle and surrounding vehicle states for position, speed, relative distance, time to collision. So everything again. So for that we need to overcome. So these are the action space. The agent can choose from keep lane and change lane left and change lane right. So DRL method, a double deep queue. What is meant by deep queue means we again it's up to reduce overestimation and improve training stability. The network outputs queue values for each possible action give the current state. So reward function, we know what the reward function means in reinforcement learning. Multi-objective reward function includes safety, efficiency and comfort. And second is we heavily penalize the risky or unsafe actions. So for the simulation setup we can just go with custom training simulation and evaluate it against rule-based methods and standard DQN method. So this is my first paper, my paper given. So for this I have limitations each. So simulation 1 3 evolution. So that means so no validation on real world data or urban driving environments. Discrete action space may not capture the continuous nature of real driving manuals. So and simplified traffic dynamics assumes non-cooperative surrounding vehicles with predictive behavior. And the final one is computational constraints, real-time performance, not fully benchmark on embedded or low power hardware. And I just given why I chose this paper. Since we are seeing lots of papers have different constraints, so yeah, I have few constraints to be overcome, and it can be overcome by this. So balanced focus on safety and efficiency, realistic problem setting, robust deep learning technique, and simplicity and practical deployability, and clear and comprehensive evaluation in alignment with my project goals. So these are the factors which make my paper better than everything. But when compared to others, like there are 8 different papers, it chooses best. And I'll just show you in every paper what are the limitations, the methodology when compared to this, and finally we just come to the conclusion. The first paper is the it's 8 different papers, and the first paper of this 8 different papers. Okay, the title of this paper is reinforcement learning based lane change and decision change for the CAVs in mixed traffic flow under low visibility conditions. And you can see the difference here. The paper addresses the critical problem in autonomous driving, making safe learning. It's similar to each other. We know what is meant by the lane changing or something we used here. for connected and autonomous vehicles, mixed traffic, and under low visibility conditions. And like we know, in those one we need just gone with the safety or something, but here we for the safety just we have the adverse conditions like weather conditions like adverse weather conditions uh, um, like this fog or rain or night. So this could be a very tough one actually. And to develop the objective is to develop the robot decision making model for lane changes in low visibility conditions, which can dynamically respond to uncertain and incomplete environment data. Methodology. Pro- Problem for formulation. The lane change decision problem is modeled as a partially absorbed Markov decision process to capture the uncertainty caused by the low visibility. That means in Markov decision process we know what is meant by Markov decision. So if we just going to choose any hot or cold, from there is an transition state into from one state to another. Like if we are going to change the lane, it's going to be a problem if there is any constraints like an obstacles there. So further we use this problem function like partially observed Markov decision and reinforced learning approach. The authors used in improved deep Q network and combined with recurrent and neural network to process this time series data. The RNN helps maintain the memory of past observations, helping the model infer current states in low visibility. RL agent is trained in a simulated environment to learn the policies for safe and efficient lane changes. Simulation environment, we're going to use it's going to be graphic simulations created with both CAVs, what we told for the earlier in for that fog and rain and human driven vehicles, and visibility levels and behavior unpredictable are modeled to mimic the real world. So this is it's one of the good paper I choose, but when compared to my paper, it's a little bit complicated and can't be getting good output. So simulation based validation, the model is tested only in simulated environments. Real world validation is not conducted. Generalization, the trained model may not generalize well to new or high dynamic real world scenarios without further training. So these are the limitations when compared to my paper, and my paper is better than this, I think so. So paper 2, deep reinforced learning lane changing decision algorithm for intelligent vehicles, combining LSTM model. Okay, this paper overview of this paper is the lane changing decision algorithm for intelligent vehicles, combining deep reinforced learning DRL with LSTM based trajectory prediction. The key innovation lies in using long short-term memory like LSTM model neural networks to predict the motion trajectories of surroundings vehicles, improving the safety and foresight of the DRL agent's decision. Overview of this paper is the lane changing decision algorithm for intelligent vehicles, combining DRL with LSTM. The key innovation lies in the using short-term memory like LSTM neural networks to predict the motion trajectories of surrounding vehicles. And again, I'm coming with the same overview, I think so. Just give it. So methodology, the trajectory prediction with LSTM, and LSTM model is trained to predict the future trajectories of the surrounding vehicles based on the past positions and velocities. The lane changing decision using DRL. So here the DDPG algorithm, deep deterministic policy gradient algorithm is used to learn continuous control strategies for lane changes. The predicted trajectories from the LSTM are used as inputs to DRL agent, giving it better understanding of future states. Reward design. These are the methodology like for everything. The methodology would be same for everything. Like for all we need to get a reward as I said earlier. So this is a custom reward function is designed to penalize the unsafe or uncomfortable actions and increase smooth, efficient lane changes. Simulation environment. The system is trained and tested in a simulated environment where multiple vehicles interact and behaviors must be adapted in real time. Limitation simulations only. The model has been validated only in the simulation, may not be robust for real world deployment, and limited generalization. The approach may require pre-training or adaptation for different road types or traffic rules. Computation cost. The combining LSTM with DDGP increases model complexity and may pose real-time computation. And coming to the next paper, its title is SGD and Triple QNet and integrated deep reinforcement enforcement learning model for vehicle lane change decision. This paper is present SDDP, QNet, and advanced lane changing decision making model for autonomous vehicles, which integrates three type of DQN, double QN, double DQN, and dual DQN into a single ensemble framework. This ensemble is further optimized with stochastic gradientism, providing adaptive decision making in dynamic traffic environments. Objective: to create a more stable and accurate lane change policy for autonomous vehicles by combining the strengths of multiple Q learning variants to reduce the overestimation bias in Q value prediction and improve the robustness of the decision in diverse scenarios. This is the methodology and triple QNet architecture assemble strategy. So for the triple Q architecture, integrates 3D RMS, as I said earlier, DQ standard Q learning with deep neural networks, and double DQ reduces the overestimation of the Q values, separates the value and advantage streams for the better policy evolution. Assemble strategy combines outputs of all three models dynamically. Uses a weighting mechanism to adjust the influence of each model based on simulation. Highway driving simulator vehicles and realistic performance from the individual models in there. So I'm going to explain limitations. Computational overhead, running three networks simultaneously increasing in the inference time. Simulation only testing. Model has not been validated in real world high fidelity physical environments, and model interpretability and integration of the multiple models makes it harder to explain the individual decision steps. Overfitting risk: complex model with many parameters may overfit specific traffic scenarios if not generated carefully. Overfitting risk: complex models with many parameters may overfit a specific traffic scenario if not generated carefully. And this is my paper 4, decision making system for lane change using deep reinforced learning in connected and automated driving. So overview of this, and the study parents lane change and decision making for connected and automated vehicles and using deep RL, and it leverages vehicular communication to share information between the vehicles and trains a DRL agent to decide how is executed and lane change safely. Objective: to develop a reliable and intelligent lane change decision system for CAVs that leverages both local sensing and vehicle-to-vehicle communication to enhance the cooperation and the collision avoidance during the lane change and mixed traffic scenarios. So methodology of this, and DRL framework utilizes the deep Q network and to train an agent to make a lane change decision based on observed and communicated traffic states, and state information includes the eager vehicle state and the speed, position, and acceleration of the state of the vehicles and the shared states of the surrounding vehicles obtained via V2V. Okay, and a communication model: vehicles exchange information such as position, speed, and intended maneuvers to assist the decision making process. The reward function designed to balance safety, collision avoidance, and safety and comfort. Negative rewards for unsafe maneuvers or near collisions. Positive rewards for successful, smooth, and lane changes. Then the limitation of this, the dependence on the V2V, the system assumes perfect V2V communication, which may not be available in all environments. This is my paper 5, and the reinforced learning decision making of autonomous based semantic segmentation. This overview of this, and this paper explores a hybrid approach that integrates semantic segmentation and reinforced learning to enhance decision making in autonomous vehicles. Instead of relying purely on low-level sensory data like LiDAR or RAM images, the system uses semantic segmentation to extract a higher level seeing and understanding before passing to the RL agent. Objective is to improve the interpretability and environment awareness in the decision making by using semantically segmented vision inputs to create more context aware reinforcement learning agent for real world autonomous driving application. The methodology of this and semantic segmentation module utilize the deep neural network like Lab V3 to extract semantic maps of the environment, including roads, lanes, and obstacles in the vehicles and the pedestrians. So reinforcement learning and deep learning, Q learning, Q network is used to make high-level driving decisions like key lane changing and lane keeping and stop or go. The RL agent uses a segmentation output as a state input, allowing more informed decisions. And the simulation implemented in a car simulator, which provides high fidelity driving environments. The vehicle interacts with urban and highway setting to train in its decision making. The reverse structure is that penalize the collisions, traffic violations, and the sudden maneuvers, and reward progress towards the destination, lane adherence, and safe driving. So limitation of this computation overhead, semantic segmentation, and networks are computationally expensive and potentially limiting real-time application. So generalization to real world, although trained in Carla, real world variation is visual input and weather condition may affect the performance. So segmentation dependency, if semantic segmentation fails are measurable. The RL agents in decision may become unsafe. The segment agent focus, the system does not பார்த்துக்கலாம், அதை கட் பண்ணிக்கலாம். The system does not address the multi-agent interaction or cooperative behavior with other autonomous or human-driven vehicles. Paper 6. So out of these 5 papers, with different papers, my paper seems like an easy as well as the best way to give a solution for the people who have been using for the first time in the to developing good movement around with the CV in the future. So like an autonomous vehicle behavior decision, the paper 6 is an autonomous vehicle behavior decision method based on the deep reinforcement with a hybrid state. Overview. This paper processes behavior decision making framework for autonomous vehicles that combines deep reinforcement with a hybrid state space composed of both semantic and kinematic information while integrating driving and risk assessment to guide decision making. The objective is to adaptability, safety, and realism of autonomous vehicle and decision making by considering both physical and as well as the semantic feature of to use driving risk as part of the input for better risk aware action in complex traffic situations. The methodology hybrid state space combines low level kinetic model with high level semantic model and includes a driving risk index computed from vehicle interaction and the potential collision, deep RL, dueling double DQL, DQ learning, and for the discrete high level decisions, and incorporate risk values directly into the safety to bias the policy towards the safer action. Simulation environment built in Sumo, simulation of urban mobility for the dynamic traffic and complex road configurations. The agent interacts with both human-driven and autonomous vehicles. The reward functions encourages progress and comfort and lane discipline and penalize the risky behavior, abrupt the lane changes and near collision scenarios. So limitation simulated testing only. The model is tested only in the simulation and real world performance yet to be valid. And scalability issues in a very dense traffic or urban intersections. The computation performance, the convergence degrade. The risk evaluation model is manually defined and may not adapt well to the unseen or unexpected traffic in the fixed risk model. Lack of cooperation. The approach focus on the ego behavior with incorporating cooperative maneuvers with other agents. So my last before paper and என்னாச்சு
மைக்கே ஆன் ஆகலடா
இதில் ஓடுதில்ல அப்போ ஒன்றும் பிரச்சனை இல்லை. டைட்டில் the paper 7 is இதில் ஓடுதில்ல ஒன்றும் பிரச்சனை இல்லை, பார்த்துக்கலாம்.
சரி ஓகே.
ஏன்னா இப்போ வாய்ஸ் ஓவர் நான் கொடுத்துக்கிறேன்ல.
இதை கட் பண்ணி எடிட் பண்ணிடு.
Okay. Um, Title Coordinated Decision Control of the Lane Change and the Car Following for Intelligent Vehicle based on the 9 series prediction and deep learning reinforced learning. So this paper proposes a coordinated decision making system that unifies the lane changing and car following tasks for the intelligent vehicles using deep reinforced learning, and it introduces a time series prediction module to forecast surroundings vehicle trajectories, which includes the guides the DRL agent in the making proactive, smooth and safe decisions. An objective to design a coordinated decision control model for both lane changing and car following behaviors to leverage the trajectory prediction for dynamic planning in real traffic environments, so improving the safety and smoothness. And the methodology for this, the time series prediction, utilizes the LSTM approach to predict the future position and the speed of the surrounding vehicles. These predictions feed into the state representation for the reinforcement learning model. DRL agent implements the double DQ network to select actions based on the predicted trajectories and the current state. Actions include accelerate, decelerate, and keep lane and change left or right. Coordinate control strategy integrates lane changing and car following into a unified action space, aims for the smoother transition and fewer conflicts compared to the treating them separately. Reward function includes the components for the driving efficiency, collision avoidance, and lane discipline and comfort. Simulation tested in the custom build simulation environment, assembling the real highway driving, evaluated against baseline DRL methods and heuristic models. So limitations, heavy computation, combining LSTM prediction with DRL increases and the model complexity with runtime. Real world uncertainty, the forecasted trajectories may not always be accurate and under the real world randomness or erratic driving behavior. Limited scenarios evaluated mainly on highway settings. Performance in urban environments with traffic signals and the pedestrians remains untested. The black box nature, like most DRL systems, interpretability of the decision making process is limited. And the final paper of this 8 different papers, and a safe and efficiently lane change decision making strategy of autonomous based on the deep RL. So here the paper was truly based on the deep RL based on the decision making for to perform and safe, efficient in lane changes on highways. It focuses on creating a deep agent capable of evaluating traffic scenarios and making decisions that maximize efficiency, safety, and driving comfort. This approach uses double DQN and uses a well-structured reward function to guide the agent's learning. Objective to develop a lane changing decision making strategy that enhance the driving safety and efficiency of autonomous vehicles, to implement the DRL agent that learns optimal lane changing policies in a simulated highway environment using observed vehicle states and interaction, to address the limitation of traditional rule based and supervised learning based methods by using interactive self-learned behaviors. And the methodology of this state space design, action space, and reward functions, algorithm use, simulation. So for the first one, includes the ego vehicle state and the relative position speed and lane. It's similar to each other. And action space, discrete actions, keep lane change and right, and reward function, safety, driving efficiency, driving comfort. Algorithm used double deep Q and to reduce the Q value overestimation and improves training stability. And a custom simulation environment mimicking highway traffic is developed to evaluate the performance of the DRL agent. Limitations, simulation only. The model is tested executively in simulation real world performance in the complex urban environments, and simplified traffic assumes predictable and rule abiding vehicle behavior which may not reflect the real world. And discrete action limitations, the use of the discrete actions limits the maneuver granularity. Real driving often requires more nuanced control. In generalization, the model may require retraining for different driving scenarios, weather condition, or traffic densities. And this is the comparative analysis for each and every paper I given. So for the first paper, I'll just explain. I'll just give an overview of everything. So for the paper one, so the sensor used for every paper is like இதை கட் பண்ணிக்கலாம், என்ன சொல்கிறதுனே தெரியலையே, இது சும்மா காமிச்சா போதுமா அதை? சரி, ஓகே. These are the comparative analysis what I given here. So for everything we need, I'll just explain, like I'll just give the software and hardware used alone, since I know about only the one thing, like where we can execute. So for everything we need and simulation for using the PyTorch and Carla. So for my project I just used Carla and I got a good output there. So limitation to be over there. So limitations and is given here and what it means and how to work on it. So for everything we need a Carla and LSDL simulator which gives you a current accuracy of the graph, how it's started from here to here and keep going on to the destination. This is my problem statement here. Autonomous vehicle must continuously assess their surroundings and make safe and efficient lane generation in dynamic and multi-agent environments. Traditional rule-based or supervised learning and approaches are often limited in adaptability and scalability and robustness, especially in complex traffic scenarios involving an unpredictable behavior from surrounding vehicles. And solution. This is the solution I have given and I got the output for that. I will show you. Implement the improved lane changing and system in Python by integrating the Carla simulator with a custom gym environment that simulates the realistic urban driving. Uses a deep reinforcement learning and algorithm inputs such as vehicle speed and relative positions and lane data. Design a modular reward function or to penalize the dangerous penalize the dangerous பார்க்கலன்னு சொன்னேன்.
வருது ப்ரோ, அதில் தான் ஏதோ நெட்டு ப்ராப்ளம் இருக்குது.
எதுலேருந்து வரல. சரி ஓகே, ப்ராப்ளம் ஸ்டேட்மெண்ட் அது இதுக்கு முன்னாடிலாம் வந்ததா? இதெல்லாம் வந்ததா கன்ஃபார்மாக?
இதுலேருந்து நீ திரும்ப
ஸோ
நடுவில் கட் பண்ணிடுது.
So these are the limitation I done with. We need to overcome this. These are the 4 limitations I kept for that and set for that. To overcome for this with my model. So simulation only validation and we need to use what it means that model was never tested outside simulation. So for this we can work on with Carla or LGSVL simulator with realistic sensors and urban settings. Like we can just give it complex reward tuning and not test in urban rewards and limited generation. So everything we need in proper movement, like as I said earlier, for an reinforced learning we need an start where we need to go development with going up and up with and reward search based, and we need to go for the reward by hitting the destination for every move we get a reward. Like then it's like we can go. So this is the problem statement. Autonomous mining must continuously assess the surroundings and make safe and efficient learning lane change decisions in dynamic multi-agent environments. Traditional rule-based or supervised learning approaches are often limited in adaptability, scalability and robustness, especially in complex traffic scenarios involving unpredictable behavior from surrounding vehicles. So for this I given a solution. Implement the improved lane change decision in Python by integrated Carla simulator with a custom gym environment that simulates a realistic urban driving. Use a deep reinforcement algorithm like SAT or DDBG from the stable baseline library. Okay, and these are the references I have given for you guys.
வீடியோ காணோம்டா. வீடியோ காணோம்டா.
வீடியோ வருது ஓடுதுடா.
ஓ வீடியோ காணோம் பாரு. என் ஃபோனில் வருது, உன் ஃபோனில் வரல.
ஓ அது ஓகே, அதை ஒன்று பண்ணோம் உங்களை பார்த்துக்கலாம். ஸோ கண்டினியூஸாக தானே போகுது, அது ஒன்றும் பிரச்சனை இல்லை. ஸோ ஓகே, these are the references for the papers I again the 8 papers references and we can look into as I given earlier. So output of this project I just brought using PyTorch and the Carla. I'm using Carla simulator. So whenever I just going on the start from the 0 and it's reach for every reaction, like every moment there will be an reward. So there is a zigzag like, and we get a signals for that. So the wave will just forms as the up and down waves, the clipping up the cliff are the rewards and it going in the linear is to reach the 80. So thank you so much for hearing this.